Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are on lecture 26 today and we are discussing about JKR contact mechanics experiments using cylinders. So, in essence we have two cylinders which with their axes parallel to each other, and we bring them in contact, and the cylinders have these properties: radius of curvature, elastic modulus and Poisson ratio, and we have this relative radius of curvature that we have defined in the last few lectures, relative radius of curvature. Then this Young's modulus, effective Young's modulus, where nu sigma 1 sigma 2 are Poisson ratios, and when you press these two cylinders the contact area increases and there is deformation of this of the surface of the cylinders because of the load, and that deformation of this surface of the cylinder in the portion in which they come in contact, okay, the profile of that deformation, total deformation, is given by this equation: nu 1 or rather V1 at z is equal to 0 plus V2 at z is equal to 0 is equal to delta is actually delta 1 plus delta 2, that is the summation of this deformation of this summation of the distance through which these two cylinders they come closer. So, this is delta 2, let us say, and this is delta 1, let us say. So, as we apply load, okay, these two cylinders come closer, and by distance let us say delta 1 plus delta 2, and as they come in contact, okay, the deformation happens at the surface, and that deformation, okay, is given by this relation where x is the distance of this particular point at which this deformation happens, and this is the deformation at z is equal to 0, that is the surface of these cylinders. So now this question is that how this deformation varies or becomes different when there is adhesion present. So, we will come to that in a minute. So, here this A as this contact radius, that can be shown to be by this relation 4 pi r by pi e star square root, okay, that we can deduce. Although when we apply the load, so we can deduce this equation by again by geometric analysis, okay, but I would like to do it in a more rigorous manner today. And so, but before that let us take a small problem and then we will go about it. Let us say a cylindrical roller with radius of 10 millimeter is pressed against a rigid flat surface with a line load of 5 Newton per meter. So, here this 1 by r is 1 by 10 millimeter, 10 into 10 to the power minus 3 plus 1 by about in infinity, and this is 1 upon meter here. So, this is equal to 0.01 meter inverse, because it is 1 by r, and here it is 1 minus sigma 1 square 0.5 whole square by E1 is 2 megapascal, 2 10 to the power 6 here, plus this is 1 minus. So, now here it is about infinity because it is rigid. So, it is infinity, E is very large. So, from here this E star will be given by 2 into 10 to the power 6 divided by 1 by 4 here. So, it is 3 by 4. So, it is 4 into 4 by 3 here. So, it is 8 by 3 10 to the power 6 Pascal. So, it is 8 by 3 into 10 to the power 6 Pascal over here, and here r equal to 0.01 meter. So, here we can substitute these quantities. So, here it is 5 Newton per meter. So, it is 4 into, it should be 5 into r is 0.01 and divided by, this is pi, and E star is 8 over 3 into 10 to the power 6 square root. So, we have to find out what will be the value over here. So, here, so we can get finally 0.1545 millimeter. So, that is the contact width that you can get. So, just to check if the units are fine, Here this P I have written it, actually I have written F here, but I think it should be P. So it is Newton per meter into meter and divided by Newton per meter square, Newton per meter square, it is square root. So this is Newton per meter, this is Newton per meter, this is Newton per, this is meter per Newton, that's fine, Newton, so it is actually meter, that's fine then, okay, we are fine. So like that, we can check also that whether we did correctly or not. So now between two cylinders at any point, as I said, that is H, that is the gap between the cylinders, okay, before they are contacted, it was given by this kind of relation. So that we, from the geometry, we had described in quite a few lectures back. And for points lying within the contact area, it was like this. This is the displacement, vertical displacement cylinder, summation of that. And outside the points lying outside the contact area, this deformation amount is actually finally larger than this. So therefore they do not come in contact, that also we have described. Now what kind of pressure distribution will result in the above deformation profile, that is the question. So now for 3D geometry, so that means when they were considering the spheres, okay, for the spheres in contact, the contact radius or contact area was circle, right. So that was a spherical geometry leading to circular contact area. And if there are different kind of pressure distributions, so the results that we obtain from elastic half space, okay, remember that we considered different type of pressure distribution, okay, on an elastic half space, we had described that quite some time back. And we remember that we discussed also different type of indenters on this elastic half space, and we obtained if the pressure is P0, it can be uniform pressure, it can be this kind of pressure, this kind of pressure. Now for this different kind of pressure distribution, the vertical displacements, they were different, right. And so that we could easily get, so we could actually relate. So we found that for the cylinders for the spheres in contact, the summation of vertical deformation of the two spheres can be written in this particular form, okay. And so then we thought that, okay, the pressure distribution between two spheres is like this. So the results that we obtain from our analysis of our loading on an elastic half space, that we could directly use when these spheres were in contact. But it is actually, there is some little bit of difficulty in using those results, okay, when a cylinder is contact, okay. So I will briefly describe that where is the problem. So the problem is something like this. Let us say that it is a 2D problem. So that means let us say this plane strain approximation that we had considered, and let us say that there is some kind of like a load distribution on this surface. And remember that plane strain approximation means this is the z axis, this is the x axis, and this is the y axis. So along the y axis I have considered this plane strain approximation, and suppose, okay, this is what in lecture 9, that if load is equal to constant p is equal to p0, then I had derived there the vertical deformation at the surface of the elastic half space like this, okay. So you go back to the lecture 9, you will see that we have derived this, okay, as long as p is equal to p0. So here if you see, it is fine, all these things are fine, but there is a constant there. So this has to be determined by considering that at an arbitrarily chosen large x, this v will be equal to 0. So we are considering constant load, let us say constant load, and we find some kind of deformation, of course, but the deformation will be 0, okay, at a distance that is much larger, okay, that is a very large value of x, and this is an arbitrarily chosen value of x where the v is equal to 0. So we do not have a definite value of the a, or therefore a definite quantity of v for a given p or p0 and like that. We are dependent on this constant over here. So in the 2D geometry, okay, this particular matter comes up, this constant c here. Similarly, if we remember that in lecture 11, okay, we had considered this kind of pressure distribution where it was a linear. So remember that I had considered the pressure distribution something like this. So it was varying linearly, okay, on x, and then it is g here, and then this was, of course, this was again a plane strain problem. So here again, okay, we could obtain this vertical deformation at the surface of this elastic half space. We would obtain that, right? But then there is an elastic constant, the integration constant, that needs to be determined, and that at that time also I had said that this c has to be chosen by depending on by considering that this v will be 0 at a very large value of x. Okay. So, therefore, in the 2D geometry this particular problem is there, that we cannot use the results that we have obtained for this different type of pressure distributions, okay, directly for solving this cylinder problem in which the two cylinders in contact. So, that was not a problem for the spherical geometry. Whatever results we obtain from this in the circular or spherical geometry for the spheres in contact from the results of elastic half space, those results we could directly use, okay, for solving or for understanding what will be the contact radius, okay, or what kind of deformation profile will be there for these spheres. We could directly use those results, but we cannot use the same things, okay, for this 2D geometry, okay, in which we have this constant integration constant c that needs to be taken care of. So, that is the problem of this 2D geometry here. So, now that aspect is taken care of, that has to be taken care of, and that is also I have discussed to some extent, but I will need to go back really repeat some of those things and quickly actually to recapitulate. So, I will do that. So, now it is problematic to identify the specific pressure distribution that would result in delta minus x square by 2r, okay, this kind of pressure distribution, okay, for this cylinders that happens by from this kind of analysis that we have already done. So, what to do? So, what has to be done is something like this. So, we actually find out the slope of this deformation. So, it will be delta v1 by del x at z is equal to 0, z is equal to 0 plus let us say del by del v2 at z is equal to 0, okay, by del of del x is equal to minus x by r. And then we remember that in some time back we had also discussed about lecture 7, okay, we had presented that gradient of deformation for a distributed normal load, okay, we had presented in absence of shear load. Now, here of course, we do not have shear load because we are considering frictionless contact, okay, and so therefore, the summation of this quantity that was could be related to the pressure distribution from this. So, that we had derived in lecture 7 and before that, okay. So, we had done that, you can have a look at those results. So, now we can match the right hand side of the two equations. So, what it means is that this equation and this equation, if we match this right hand side, so what we have here is actually this. So, Ps minus a to a x minus x will be equal to, okay, pi e star by 2r, because this pi star goes over here. So, it is x by r, you get this result. So, in a sense that we do not deal with the vertical deformation that happens in the cylindrical geometries or two cylinders in parallel in contact, but we deal with the gradient of that or the slope of that, right, that is what we are doing. And then we are relating to this relation in which you see the right hand side is the solution of this integration, and so what is unknown here, this pressure distribution over here, that has to be found out, okay, and that can be found out, and we have done, so we have presented these ideas earlier. So, what we said is that there is a general solution of this kind of problem, and the general form of the problem is also given here. So, it is general form for something like this. So, here this left hand side is the same over here, and the right hand side we have, let us say this x is to the power n and pi e star, this is e by 1 minus, actually I should say sigma square, okay, this is sigma square or e star, pi e star by 2, and then we have got this n plus 1, okay. So, this is the general form of this kind of curved surface. So, curved surface, of course, we have got a parabolic form, but here this is a general form, and the general form is given as b x to the power n plus 1, and you remember that I have described this z is equal to b x to the power n plus 1 in while discussing these things in the lecture 7 or so. And now, when we find out the slope of that, we get something like this. So, here to match it with the problem that we have, here you see that this pi a star by 2 into n plus 1. So, n is actually 1 here, right. So, we have n is equal to 1. So, n is equal to this quantity is 2 here, 2 by 2. So, b will be equal to 1 by 2 r, okay. So, if I match, okay, this quantity with this quantity over here, Okay. So, we have B is equal to 1 by 2 r and n is equal to 1. So, this is the way that the general solution that is available for this kind of problem that we can make use of. The general solution of this problem has been given by mathematicians. So, this particular functional form comes out to be like this, where this p of x will be equal to like that. So, now we know n is equal to 1 where for your case, and then b is equal to 1 by 2 r, that we have already obtained here, and then I n, it is a function of x. So, x, remember here capital X means x by a. So, this is the non-dimensional form, that is all it is, and here we have n is equal to 1. So, we need to consider only 2 terms over here, and then capital P is the total amount of load that has been applied. So, now n is odd, with the for n is equal to even also there is another form that also I had given. So, for n is equal to 1 here, okay, we will have I1 is equal to pi, and let us see, write it x by a square minus half, that is it. Here I1, so I1, so therefore P of x, okay, will be minus of, this is E star is E by 1 minus sigma square Poisson ratio square, n is equal to 1. So, n is equal to 2 here, and b is into 1 by 2 r. So, let us write it over 1 by 2 r. A is a and it is square. So, it is square here, and there is a 2 pi here, 2 pi here, and then we have got this pi here, and I have just obtained x by a whole square minus half by square root of a square minus a square, okay, plus this is p by pi and square root of a square minus x square. So, this is the form of the pressure distribution. Let us write it little bit in more compact form, and let us get rid of these terms which can be cancelled out. So, here let us write it, this is 2 here, this is 2 here, let us take a inside. So, it will be, let us say it will be minus of, this is E star divided by r here, and this is 2 here is remaining. So, let us have this 2 here, and this a square goes inside, let us say. So, it is x square minus 1 by 2 a square, and this is 1 by square root of a square minus x square, and plus this is p by pi into square root of a square minus x square. So, little more compact form. So, let us say I write it here 1 by square root of a square minus x square. Let us see here p by pi. So, let us say pi is here, let me write pi here, then it is p here, and then plus here, and let us say that this is actually equal to here. So, let us say 2 a square. So, let us say that I take 2 a square out. So, it is e square, okay, 2 a square. So, it is x square minus 1 by 5, 1 by 2 a square again. I made a mistake here. So, it is x square my a square by 2, sorry about that, I should have written here a square by 2. It is x square by 2 here because I am taking a square inside. So, x square minus a square, so right. So, it is then 2, so it is x, it is plus, I am taking, so it will be a square minus, so e square by 4 r, e star by 4 r, and here it will be, let us say a square minus 2x square, like that. I hope I have done correct. So, p by pi into square root of a square minus a square. So, I have taken pi also. So, pi should also be here. So, here, and then this is fine, and then minus, it is 1 by 2, 1 by plus 1 by 4 here, that is fine, and this is a square. So, a square goes over here. So, 2 here, 2x square, yeah. So, it I think is fine. So, like that. So, the pressure distribution, okay, that will lead to that kind of deformation profile is something like this, right. It is something like this. So, here I have taken the minus sign here. So, that is fine. So, it is like that. So, now the question is that what is A and what is yeah. So, Px is of course is defined, but what is not known is what is the value of A that will be attained in this process in this particular case. So, that is not known, capital P is known. So, capital P is the amount of load that has been applied. So, when we apply the load, okay, this particular contact area increases, remember there is no adhesion yet. So, the contact area increases and certain amount of A value is chosen, gets chosen, right. So, this A has to be determined, and So, in this equation expression of the contact width is still unknown, basically that. So, unless we know the A, we will not be able to find out what will be the pressure distribution over here. So, that will remain unknown. So, in order to find out that, we have to consider once again the physically what exactly is happening. So, now we have got these two cylinders which are in contact over here, and we have applied some amount of load. So, the contact point will be something like this, and as you can see that when you apply the load, the pressure should be maximum over here and that should decrease. Okay, this Px at the max should be maximum over here and that should decrease, and at the contact point, okay, at x is equal to A, the pressure should be equal to 0, because there is no other adhesion or anything, okay, no interaction between these two surfaces. Okay. So, therefore, we can consider this boundary condition that at x is equal to A, this Px, okay, that should become actually equal to 0 or positive, because there is a compressive pressure here. So, pressure should be positive or like that. So, if we consider that, then we can get some idea from here that what should be the A. So, it is like this P, capital P minus pi E star by 4r, okay, and x is equal to A, 2a square minus a square. So, it is a square. So, that should be equal to 0 or greater than 0. So, from there we can say that A goes as 4r into P divided by pi and E star square root. So, Newton per meter, P is Newton per meter, R is meter. So, it is Newton here, this is Newton per meter square. So, the meter square is in the numerator, square root of that meter, fine. So, 4r P by pi star, that should be the contact radius, and we have actually remember that few slides back I already had presented this particular result, that contact width, okay, increases with pressure square root, okay, for the cylindrical geometry. Now, for a spherical geometry, remember, so for a spherical geometry, okay, P goes as 1 by 3 here, geometry. This A goes as P to the power 1 by 3, okay. For a cylindrical geometry, A goes as P to the power 1 by half, okay. So, that is the way it happens. So, that is what the pressure distribution is. So, therefore, the total pressure has to be equal to, so I have already said, so it should be equal to pi E star a square by 4r, and finally, okay, by using this quantity, that P is equal to this and A is equal to, we have already obtained. So, finally, if I substitute for this P over here, okay, and then we will get this Px as equal to this quantity we will get, okay. We get it very nicely, this particular result, yeah, pi star like that, we get it like that. So, you see this kind of pressure distribution, okay, that is the Hertz pressure distribution that we recover, okay, by this analysis that we can get. So, now the question is that now let us say there is actually adhesion the surface. So, yeah, so here the same thing, that the total pressure is like this, the pressure distribution in the contact area is like this, and for a two spheres in contact there are also pressure distribution like that. So, here it is x because in 2 dimension, and here it is the 3 dimension. So, it is r, it is like the spherical geometry, it is r. So, now the question is that how do I consider the adhesion between the two surfaces. So, when there is adhesion between the two surfaces, it looks something like this, as I have already discussed for the spherical geometry. So, let us say that it is in contact like that, and now it was Hertzian contact, but now that there has been adhesion between them, there has been deformation, because the adhesion pulling force actually tends to deform the surface of these two cylinders, let us say, and it will form something like that. So, this is in essence what we have is a crack opening situation over here, okay. So, in the fracture mechanics, okay, language, we will have what is known as the crack opening, and in fracture mechanics concept, so we will have to borrow some idea from fracture mechanics over here. So, what they do is that they find out the stress around a crack tip. So, this is a crack, let us say, okay, two materials are being opened like that. So, this is one material, this is another material, and they are applying some load over here, they try to like open it. So, this kind of crack opening situation, they call it mode 1 crack actually, mode 1 crack. And then there is another way to open the crack, and suppose it has got one material is something like this, another material is something like that, and let us say they apply the load something like that. This is in shear. So this is called the mode 2 crack. So over here we do not need to worry about, let us say, mode 2 crack, because we do not consider that. Let us say it is about mode 1 only, and in that mode 1 what is the stresses that has developed in the crack. Now when there is a crack develops and the radius of contact is close to 0, the stresses actually are infinity, and so therefore stresses therefore we can write this expression in terms of stress, because it is compressive pressure, but so when there will be adhesion between them, there is a pulling effect, and so therefore there is a crack situation. So the stress there will be maximum at the crack tip or like that. So basically stress singularity will be there. So let us write this expression little differently. Now when there is present, when we have this adhesion present, then we cannot use that boundary condition that we did, that the pressure Px has to be 0 at the contact line. No, that is not possible, because there is adhesion between them. So it has to be stress singularity has to be there. So therefore we cannot write that. So we can write this expression over here somewhat differently. So let us say I write it like this, Px or rather I will write sigma x. So that is the stress actually. So it is actually minus of Px. The stress is negative of pressure, so it is minus, so 1 by pi, and this is square root of a minus x into a plus x. And so here yeah, it's like that, and let us say then I write here capital P minus, this is pi, this is E star by 2r into x square minus a square by 2. So I will show you that there will be stress singularity, and how to take care of stress singularity, and how fracture mechanics idea can be used to obtain the what is known as the strain energy release rate. So for a brittle fracture, strain energy that is given to the crack tip, that's actually is spent in creating these new surfaces, so that can be equated to the work of adhesion. So I will take up that how that use the fracture mechanics ideas for obtaining the work of adhesion in the next class. Thank you for your kind attention.